All right, good morning. Uh, Continuing on with what we have regarding functions, and this time working with quadratic functions. Uh, okay, we have on page 249, okay, and I'm going to do a little bit of a modification with some of the problems in the mix. And for what we have in number 10, okay, we're looking at the features of a quadratic function which we have given in the form of k of x is equal to 2 times the square of the binomial x minus 3 followed by the subtraction of 2. And again, what we have laid out for k of x, okay, is in vertex form. And now for the general layout, what we have for the vertex form, again, you have a times the square of the binomial x minus h followed by k. And in terms of the behavior of the graph of the function and the location of the activity, this is going to be contingent upon the values of a, h, and k. And just looking at what we have among the features. Okay, so we go ahead and look at solving for a, h, and k. Now we have for a, we have that a is equal to 2. And again, for x minus h, I'm just going to mention, again, now we're not working with, strictly speaking, the zero product property, but I just wanted to mention, like if you were to take that which represents x minus h and set equal to 0, you would have the x is equal to h. So this would form the axis of symmetry, which we have at x is equal to h, and h again, or x is equal to h, that would be the first coordinate in the vertex. Okay, so we have for x minus h, this is represented by x minus 3. So we have x minus 3 is equal to 0. And we have the x is equal to 3. Okay, and so we want to have for the attainment of what we have for this x, this will also be the same as what we have for h. So we have the x is equal to h is equal to 3. And for what we have in the case of k, again, we have the subtraction of 2 at the end. So we have that k is equal to negative 2. And just for the defining characteristics, okay, so we have, first of all, in terms of the direction that the graph is going to open, okay, so we have that a is equal to 2. And since 2 is a positive number, okay, the fact that a is positive, this signals that the graph is going to open upward from the vertex. And now, in terms of what I mentioned the other day, okay, we had the parts to be rearranged, okay, and so just kind of moving f out to the front. F is just asking for the axis of symmetry. Again, so you have the axis of symmetry, x equals h. So the axis of symmetry in this case, okay, we'll have that x is equal to 3. And for what we have in the case of part B, okay, we have for the vertex, once again, the general coordinates we have at h and k, and the location of the vertex will be situated at 3, negative 2. Okay, so with the attainment of the values of a, h, and k, okay, we have, again, the axis of symmetry, the vertex, and the direction to which the graph is going to open to already be determined. And now, for what we have concerning the added construction parts, and we have with the intercepts. Okay, so we have with the x-intercept, again, we have the general coordinates, okay, to be x0. And for what we have here, okay, now, again, we're looking at solving for x whenever y is set equal to 0. Now, again, for this function, y is represented by k of x. So in this case, right, so we're looking at solving for x, and again, that which represents y, okay, is going to be set to 0. So the 0 is equal to 2 times, okay, the square of x minus 3, followed by the subtraction of 2. Okay. And so now we have our x expression, okay, in the form of the binomial x minus 3, and there's activity around this. You have multiplication by 2, the binomial is raised to the second power, and we had the subtraction of 2 to follow. So we have quite a few 2's in the mix. And if we isolate the variable expression, okay, we can proceed by undoing the subtraction upon adding 2 to both ends. And so we're going to have in the rewrite, okay, so you have 2 is equal to 2 times the square of x minus 3 and looking at dividing the equation by 2. Okay, so right now we're going to have 1 is equal to the square of x minus 3. All right. And, okay, so we had the setup whereupon we can perform the square root property of equality. And what I'm going to do here is I'm just going to switch sides, kind of like going from b is equal to a is equal to b format. So you have the square of x minus 3 is equal to 1. And we have with the square root property of equality, again, you have like if x squared is equal to p, then you have x is equal to plus or minus the square root of p. Okay, so here we have x represented by x minus 3. So we're going from the square of x minus 3 to just plain x minus 3. And we have is equal to plus or minus the square root of 1. So you have p represented by 1. And so we're going to have x minus 3 is equal to plus or minus 1. And so we have 2 outcomes here for x. One is going to come from setting x minus 3 equal to negative 1. And we have at the higher end, okay, we have x minus 3 is equal to positive 1. And so looking at solving for x in both of these equations, okay, so if we add 3 to both sides in the equations, okay, so we have for x minus 3 is equal to negative 1, okay, we have that x is equal to 2. As for x minus 3 is equal to 1, okay, we're going to have that x is equal to 4. And so we're going to have a couple of x-intercepts. Okay, so you have for x equals 2, if I express in coordinate fashion, I have 2, 0. Remember, each x-intercept is of the form x, 0. And with x at 4, we have another x-intercept, which we will have at 4, 0. Now, for what we have for the y-intercepts, okay, you have a bit of a role reversal in terms of what we're solving for and what we have to set equal to 0. Okay, and for what we have in the case of the y-intercept, okay, so again, y is represented by k of x, okay, and now we're setting x to 0. So in this case, okay, we'll have that y is equal to k of x. Now k of x is going to be set to k of 0, since x is going to be set to 0. And for what we're going to have to occur in following through, so you have 2 times 0 minus 3 to the second minus 2. And we have 0 minus 3 is negative 3. negative 3 squared is going to be at 9. And 2 times 9 is going to be 18. And for what we have in the follow-through, 18 minus 2 becomes 16. So the y-intercept is going to be situated at y is equal to 16. And in terms of the location in the xy coordinate system, okay, this is going to be at 0, 16. So we have 3 intercepts, 2 on the x-axis and 1 on the y-axis. Okay, so in terms of the dynamics, okay, that have been carried out. So this is our quadratic function. Again, we have the vertex, 2 intercepts, and a y-intercept. And again, the graph opens upward from the vertex. And again, the graph of the function is a parabola. And the axis of symmetry is going to divide this into 2 equal halves. And that will mirror each other about this dividing line. Okay, so we have, at least in terms of what we have from a visual perspective, okay, and so we got and if you notice, okay, we have with the components here. Okay, so you have so you got for the parabola, you have this to represent y, or k of x is equal to 2 times the square of x minus 3, followed by the subtraction of 2. And now, and again, for the axis of symmetry, okay, this is in reference to x is equal to 3. Okay. And if you notice, okay, we have moving up. Okay, so you have the axis of symmetry. We have x is equal to 3. So if I were to go up, notice you have the x-intercepts equal in distance from this axis of symmetry. Sorry. And so we have in this one. Okay, all right. So to get that, okay, so you have x is equal to 3. So you have one space to the left, one space to the right. And if I were to go up the axis of symmetry, and we have level with the y-intercept. So we have 3 spaces to the left with the y-intercept. And then we have, without even having to do any calculations, you can go 3 spaces to the right. And if you were to supply a 5th point, you will have 6, 16. So you have this point level with the y-intercept. Again, the x-intercepts are level with respect to each other. And again, these points here, 0, 16, 6, 16, that pair is equal in distance from the axis of symmetry. 2, 0, 4, 0, also equal in distance. And again, we had the parabola opening up from the vertex. And so with the way that the vertex is situated, okay, that is going to be regarded as the function's minimum. All right. And now, for what we have in the case of the next item, and we have for number 12, okay, and so we have a function r of x, and that is set equal to 1/2 of the square of x plus 2. Okay. I'll just go ahead and re-emphasize in case you have y is equal to r of x. Is equal to 1/2 of the square of x plus 2. And just for the general layout, in this one case, you have y is equal to r of x. And again, we have is equal to a times the square of x minus h, followed by the addition of k. All right, so we have just for the items, okay, so we have in front of the binomial, okay, we have the number 1/2. So we have the a is equal to 1/2. And for x minus h, okay, we have represented by x plus 2. And if I set this equal to 0, so we have x is equal to -2. So we have that x is equal to h is equal to -2. And for the k value, okay, we don't have anything added or subtracted. So there's a void here. So we have that k is equal to 0. Okay. And so we have in terms of the shape of things. Okay. So you have a is equal to 1/2. Okay, now it's a smaller number than 2, but it is still a positive value. So in terms of the activity, okay, so the graph is going to open upward. And for what we have in the case of the axis of symmetry, okay, so we have x is equal to h, and again, that value we have at -2. And for what we have in the case of the vertex, okay, so for the vertex hk, okay, I have h at -2, k at 0, and it's going to turn out that the vertex and the x-intercept are going to end up as one and the same. Okay, all right, and in terms of the intercepts, now for the x-intercept, I'll just go ahead and kind of lay this out. It's going to have an element of repetition to it. So we have with the x-intercept. Okay, so we have, again, so we have r of x is equal to 1/2 of the square of x plus 2. And once again, okay, for that which represents y, okay, that is going to go to 0. Okay, and okay, so just in terms of following through, okay, so if I multiply both sides of the equation by 2, okay, just so as to get rid of the 1/2. Okay, so 2 times 0 is 0. Got 2 times 1/2 is 1, and then we have is equal to the square of x plus 2. All right, and I can just switch the order once again. Let's have the square of x plus 2 is equal to 0, and just re-entering the phase of utilizing the square root property of equality. So if we go from square to first order in x plus 2, and guess what? Okay, now square root of 0 is just plain 0. Okay, so for what we refer to as plus 0 minus 0, those are going to be the same. Now there is a thing in calculus referred to as infinitesimals, like have like -0.0000 and positive 0.0000, but that's a totally different topic. And so for x plus 2 is equal to 0, we have that x is equal to -2. So again, for the x-intercept, okay, we have x equal to -2. And for what we have in coordinate fashion, okay, we're going to end up with the ordered pair once again, -2, 0. So the vertex and the x-intercept are going to be one and the same. And for what we have regarding the y-intercept, so again, we're solving for y as x is set to 0. So we have that y is equal to r of x, Okay, so x is going to be set to 0. And we have 1/2, and x plus 2 becomes 0 plus 2. This will be to the second. And we have 0 plus 2 is 2. And we're going to square this out. So 2 squared is 4. And so we have 1/2 of 4. And 1/2 of 4 comes out to 2. Okay, so you had an x-intercept of -2, 0. And for the y-intercept, okay, so y is equal to 2, and as an ordered pair, we're going to have this situated at 0, 2. All right. So for what we have in the dynamics, okay, so you have quadratic function again, and the layout just as was the case number 10. Okay, we had in vertex form. Again, the leading coefficient is positive. The graph opens up, and again, the axis of symmetry, we have x equal to -2, and again, what we have for the axis of symmetry, what x is equal to, is also going to be the first coordinate in the vertex, and the vertex which we have simultaneously to be the x-intercept, we have at -2, 0, and the y-intercept again we have at 0, 2. And in terms of the activity that we have regarding this particular function, okay, so we have for y is equal to 1/2 of the square of x plus 2. Okay, so again, you have the vertex at -2, 0, and the graph opens upward, okay, from that location. And again, just for the activity, again, you have your axis of symmetry. So you have x equal to -2. And again, for the spread in the graph of the parabola, again, you have at each location along y, okay, you have equal in distance from this visual vertical dividing line. Okay, so you have the y-intercept at 0, 2, and equal in distance on the other side we have -4, 2. And if you were to throw in any other points, okay, like 4, 18, okay, you have to belong to the graph of the function, and this is located to the right and equal in distance. Okay, so you have like 1, 2, 3 squares, and each horizontal square spread you have in increments of 2. And you have 3 squares to the left, or 6 units to the left of x equals -2, so you have -8, 18. Okay, so so these points would be among infinitely many others that will make up the graph of y is equal to 1/2 of the square of x plus 2. All right. Now, regarding what we have concerning the next items, and tell you what, for 2 out of the 3, I'm going to just look at the translation from the standard form to the vertex form. And for the remaining one, I think I'm going to probably save this one for last. And in these problems, okay, now you're going to have x-intercepts to be irrational roots. And for what we have in the case of what we have regarding number 17, okay, so if I'm going from standard form to vertex form, okay, and we have n17, okay, so I have p of x is equal to 3x squared minus 12x minus 7. Okay, so I got p of x equal to 3x squared minus 12x minus 7. Okay, and okay, so again, this is going to be the standard form. and as we proceed to translating what we have in vertex form. So I'm going to put the parentheses around the variable terms and separate from the constant, which we have in -7. So you have p of x. Okay, so you have grouping parentheses around 3x squared minus 12x. Okay, again, we have followed by the subtraction of 7. Now, there is a stage, once again, with the completion of the square. And do not perform the completion of the square until you have the first term in the parentheses to be just like x squared or y squared. In other words, you want just x squared inside the parentheses. So what I'm going to do here, we got 3 in the way. So if I factor out 3, okay, so you have p of x. So if I factor out 3, just draw this out to the front. So you have 3 times the quantity of x squared, and 3 into -12x. Okay, and that is going to be -4x. Then we have -7. And with the leading term inside the parentheses at x squared, I can now perform the completion of the square. Okay, so 3 times the quantity of x squared minus 4x. Now, for what we have regarding completing the square, again, if the leading variable term is just x squared, okay, what I'm going to do here is that I'm going to take the coefficient that is next to the first order variable. In this case, we have -4. And with the completion of the square, doesn't matter what number it is, whether it's odd, even, positive, negative, fraction, whole number, rational number, irrational number, you're going to take half the value that is next to x and square out. So half of -4 becomes -2. And the square of -2 is equal to 4. And looking at what we have in the mix in terms of the change up that will be occurred, or that will occur, okay, once we have 4 to enter the scene. So we'll have 3 times the quantity of x squared minus 4x, and we're going to make what we have in parentheses into what is going to be a squared trinomial. Okay, all right, so I'm adding 4 inside the parentheses at the front. Okay, now I want to keep everything in balance or in line with the original standard form setup, where I'm still going to have 3x squared minus 12x minus 7. And if you notice, okay, we have at the front, as we're adding 4 within the parentheses, you're not just adding 4. Instead, you have, thanks to the coefficient 3 that was factored out, you're actually adding 3 times 4, which is 12. Okay, so I'm going to have to offset this newly created imbalance by taking away 12 at the end. Okay, so adding 12 at the front, okay, and keeping it in balance with subtracting 12 at the back. Okay, and so for what we're going to have here, we have p of x is equal to 3 times the quantity, okay, we have of x squared minus 4x plus 4, and -7 minus 12, okay, this will become -19. And you can momentarily check what we have here. Okay, so you got 3 over x squared is 3x squared. 3 over -4x is -12x. Now 3 times 4 is 12. 12 minus 19 goes to -7. So we have this rewrite, okay, keeping everything in balance in comparison to the original setup. Now, we have with x squared minus 4x plus 4. Again, we're going to have a squared trinomial. And now for x squared, okay, this is going to be the square of x. And what we had in terms of what led to the formation of the addition of 4. Okay, again, we had just subtracted, or I should say, taken the negative of 2 and squared out. And whatever we square is going to re-enter the scene. So we're going to have for the vertex form in this case, and we had that p of x is equal to 3 times the square of x minus 2 followed by the subtraction of 19. So like your a would be at 3, your h value would be at 2, and your k value would be at negative 19. And we will look into number 18, but I tell you what, if we look into number 20, okay, this one kind of a different one here. And this time we had the function in the form of d of x. And the standard form, okay, we have negative 3x squared minus 9x plus 8. Again, this is the standard form. And just as we started out separating the variable terms apart from the constant for p of x, we can do likewise with d of x. So you have negative 3x squared minus 9x. Okay, those are the variable terms. And for what we have inside the parentheses, we don't have x squared as the first term. Instead, we have minus 3x squared. So at the front, I'm going to factor out negative 3. And that is so as to ensure that the first term in the parentheses will be x squared. Okay, so for d of x, now we have negative 3 and we have times the quantity. Okay, so we have x squared. Now negative 3 into negative 9x, okay, that's going to be a positive 3x. And once again, we have followed by the addition of 8. So you can double check negative 3x squared. Negative 3 over 3x becomes negative 9x. And again, we have plus 8. Now, we're at the stage now where we can complete the square. So for what we have regarding the completion of the square. Okay, so again, we have inside the parentheses, we have x squared. For the first order x term, again, we take the coefficient that is next to x. Again, so I'm still going to take half of this. After taking half, okay, I'm going to square out. So you have 3 divided by 2. Okay, we have 3 halves squared. And 3 squared is 9. 2 squared is 4. So I'm going to have, upon completing the square, I'm going to end up with the fraction 9/4. So we have, in terms of what will be done here, so you have with d of x, we have negative 3. We have times the quantity of x squared plus 3x. And inside the parentheses, okay, we have the application of 9/4. And this is going to form a square trinomial. And we have plus 8. Now just, again, we're adding not just the completed square value, okay, at the front. Instead, you're taking a multiple, just like we added 4 inside the parentheses, but collectively you wound up adding 12 at the front. Now, for what I have this time with -3 in front of the parentheses, what I'm doing in this particular situation is that as I'm adding 9/4 inside the parentheses, what I'm doing in effect is that I'm not adding 9/4, but instead -3 times 9/4. So essentially I'm adding -27/4 or subtracting 27/4. So to override this newly created imbalance, which is upon applying -27/4 overall at the front, and we have to override this deficit that is created by adding 27/4. So by adding 27/4 to 8. So we have d of x. Okay, so we have -3. Then we have times x squared plus 3x plus 9/4. I don't know why I put the square here. Okay, so we have -3 times the quantity of x squared plus 3x plus 9/4. Now I'll just mention, just kind of moving over to the side here. So for 8 plus 27/4. Think of this like 8/1 plus 27/4. And adjusting 8 in terms of fourths. Okay, so 8 is going to become 32/4. And adding to 27/4. So we have 59/4. Okay. So we're going to have -3 times the quantity of x squared plus 3x plus 9/4. And then for 8 plus 27/4, okay, we're going to have at 59/4. And for what we have in the case of the vertex form, so you have d of x, okay, so you have -3. So your a value is going to be at -3. And your k value is already going to be at 59/4. And for x squared, again, this is going to be the square of x. And in terms of completing the binomial, again, we go back to the completion of the square activity. So in this case, we have the square of 3/2. And so what I squared out in the completion of the square process, okay, that is going to re-enter the scene. Okay, so when all is said and done, okay, we're going to have for the vertex form, we'll have that d of x is equal to -3 times the square of x plus 3/2. And we have followed by the addition of 59/4. And once again, that is going to be the vertex form. Okay. All right. So there are lots of mechanics involved especially if you're translating from standard to vertex form, and then identifying the other stuff like the intercepts. And we'll look at number 18 later on. But what I want to mention, okay, just to kind of go into other types of polynomial functions, and we have in the layout, and just kind of revisiting stuff like the zero product property and the FOIL method. So we'll just call this particular part, okay, forming polynomials. From given zeros and multiplicities. Okay, and now in terms of application, multiplicity is just going to enter the scene a little bit later, but I'll go ahead and give a definition. Okay, now for the multiplicity of 0, you're looking at exponents. And the multiplicity of 0 in f of x, by definition, okay, that is going to be the degree to which the factor corresponding to that 0 okay, so you have the degree to which the factor corresponding to that 0 will be raised. Whenever f of x is in factored form. Okay. And we'll look at multiplicity shortly. Okay, but right now, for what we have in the case of forming polynomials from given zeros and multiplicities, and say we're looking at determining f of x in both factored and expanded form. Say we have given the following. Okay, so we have we'll say we have in the layout. Okay, so we have for the zeros. Okay, now I'm going to start out with the zero values. Okay, we'll let those be of multiplicity 1. So you have the zeros. Okay, so we'll say that we have so you have -4 and 5. And we'll say that the degree of the polynomial function, okay, we're going to have this where the, okay, so since these are going to have multiplicity 1, and again, I'll explain that in just a moment, we have 2 zeros, and the number of zeros we have and the degree will match up. Okay. All right, and just for the setup, okay, so you got your zeros at -4 and 5, and think of this as taking the zero product property and working in reverse. Okay, say if you have like x is equal to -4, and we have x is equal to 5, think of it kind of like working backwards. Okay, so if I were to set the equations to 0, so if x equals -4, add 4 to both sides. So I have x plus 4 is equal to 0, and if I have the x is equal to 5, and say if I subtracted 5 on both sides, I will have x minus 5 is equal to 0. So you would have your factors at x plus 4 and x minus 5. So you have for the factored form, okay, or one factored form anyway, you would have that f of x is equal to, okay, we have from -4, we can say that stems from the factor x plus 4, or any direct multiple of this. And for x minus 5, okay, again, the 0 of this would be x is equal to 5. So you have x plus 4 times x minus 5. So this would be a factored form of what we have for a polynomial function that will have -4 and 5 as zeros. Now, what I mean by expanded form, okay, so if I take what I have here, so I have x plus 4 times x minus 5, and if I look at taking the FOIL, so you have x times x is x squared. Outside product, you have x times -5, so we have -5x. Inside product, okay, we're going to have 4x. Last product, we have 4 times -5, so this would be -20. And as I combine the like terms with -5x and 4x, we're going to have the expanded form of this same polynomial function. Whereupon we're going to have the f of x is going to be equal to x squared minus x minus 20. Okay, so for what we have here in the expanded form, so you have x squared minus x minus 20, and just kind of looking at what we have here, if you were to set x squared minus x minus 20 equal to 0, now the polynomial is of degree 2, and that's indicated by the highest order term that we have in the variable x. So we have x to the second, and again we have, if I were to set this trinomial equal to 0, like again what would be a quadratic equation, and I factor, I would have this as the factors and -4 and 5 as the zeros, in this case the solutions. Now for what we have regarding multiplicity, and let's say if we have something like for your zeros, okay, And we'll say that we have 0. So we have multiplicity is equal to 2. And we'll say that we have, let me change that. We'll say 0 have a multiplicity of 3. And we'll say for the other 0, we'll say we have negative 2. So let me change that. We'll say we have negative 4. And we'll say that multiplicity is going to be equal to 2. And we'll say that we have for the degree of the polynomial, okay, so you have a 5th order polynomial. Okay, now we have corresponding, okay, to our zeros, you have 0 and negative 4. So we have in these now 0, we can say this is going to stem from having set x equal to 0. So from 0, okay, we have x factor, and for negative 4, okay, we would have stemming from x plus 4. And if we had only 0 and negative 4 mentioned, okay, so if you have x equal to 0, we have 0 as the value. And if x plus 4 is equal to 0, we have x is equal to negative 4. Now for multiplicity, again, by definition, this is going to be the degree to which the factor corresponding to that 0 will be raised when the function is expressed in factored form. So we have here, for 0 we have x, but with a multiplicity of 3, you have not just x, but x to the 3rd. From negative 4 we have x plus 4, but with negative 4 consisting of a multiplicity equal to 2, we're going to have not just x plus 4, but x plus 4 raised to the 2nd power. Okay, so we have, in the case of the factored form, so you have f of x, okay, so you have is equal to x to the 3rd times the square of x plus 4. And if we look at expanding what we have here, okay, so for the square of x plus 4, okay, so that's going to be x plus 4 times itself. And I can multiply gradually from left to right. Okay, so you have x cubed over x plus 4. Okay, so this is going to be x to the 4th plus 4x cubed. And we have times the quantity of x plus 4. Again, I clustered these two factors together, multiply, and we have in foiling out, so you have x to the 4th times x. Okay, so this will be x to the 5th. Then we have x to the 4th times 4. So you have 4x to the 4th inside product. Okay, we're going to have it 4 times x to the 4th. And then we have 4x cubed times 4. So this will be at 16x cubed. So we have for the expanded form, as I combine the terms in the middle. So we have f of x is equal to x to the fifth. We have plus 8x to the fourth. Plus 16x cubed. Okay. Now, in terms of where we can have zeros to be a bit drawn out. Now, let's say we have zeros. Okay, we'll say we have the number of zeros and the degree to be the same. Okay, we'll say we have with the zeros. We'll say we have -1, 1. Let me do this. Let's say we have -1, 4, 2, and -3. All these will have a multiplicity of 1, meaning that you're not going to take any of the corresponding factors and raise to a higher power. Okay, so we have in the set, so for -1, we can say this is going to stem from x plus 1. Okay, so we have with 4, we say this is going to correspond to x minus 4. For 2, we say this comes from x minus 2, if you were to set to 0. And with -3, we can say this comes from a binomial that you would set equal to 0, such as x plus 3. Yeah, if x plus 3 is equal to 0, x equals -3, and x minus 2 leads to 2, x minus 4 to 4. And if I set x plus 1 equal to 0, okay, I would have the 0 value at x equal to -1. Okay, so we have as a factored form, okay, so we have for f of x, so I'm just cluster together. So we have x plus 1 times x minus 4 times the quantity of x minus 2. And we have times the quantity of x plus 3. Okay, so this is one way that the factored form can be expressed, and all of these zeros, okay, we just had those as a multiplicity of 1. So all these factors here will be a first degree. Now, if I'm looking at expanding the form, what I can do here, I'm just going to do a little bit of color coding here. Okay, so if I cluster, if I just FOIL out first factor, so you have x plus 1 times x minus 4. So this will come out to x squared minus 4x plus x, which is going to be -3x. We have minus 4. And say if I multiply the last two factors, so this would be x squared, and got plus 3x minus 2x, so this would be plus x, and -2 times 3. Okay, so that is going to be at -6. And if I multiply together, again, there are two ways that you can go about utilizing the FOIL method. Okay, one is just taking the conventional FOIL method, but once you go beyond binomial expressions, this is where the geometric layout for some can be kind of a visual benefit. And it doesn't matter which terms you have as the column headings and which you have as the row headings. If I just let x squared minus 3x minus 4 be the column headings, and have x squared plus x and minus 6 be the row headings. Okay. So you have just in the with the box method, or what it's also referred to as the geometric approach. So looking at the corresponding parts here. Okay, so if we go down one column at a time, so you have x squared times x squared. So this would be x to the fourth. Then we have x squared times x. So this would be x cubed. And we have x squared times negative 6. So this would be minus 6x squared. Now for the second column, we have x squared times negative 3x. So we have minus 3x cubed. Then we have x times negative 3x. So we have a negative 3x squared. Then we have negative 3x times negative 6. Negative times negative is a positive. So this will be a plus 18x. And for the last column, okay, so we have x squared times negative 4. So we have minus 4x squared. X times negative 4. So we're going to have at negative 4x. And then we have, last product, we have negative 6 times negative 4. So that's going to be a positive 24. And so just looking at what we have upon itemizing. So just looking at it, highest order term, okay, we have an x to the fourth. And next, okay, I have 1x cubed and a negative 3x cubed. So that would be minus 2x cubed. And then we have in the squares. So you have a bit of a diagonal pattern. So you got negative 6 minus 3 minus 4. So it'd be minus 13x squared. And then we have in first order in x, we have positive 18x minus 4x. So that will leave us with 14x. And then we have left over. Okay, so we have with a constant. Okay, so that's going to be 24. So we have for the expanded form. Okay, so we're going to have f of x. Okay, is equal to x to the fourth minus 2x cubed minus 13x squared plus 14x plus 24. Okay, and so that would be the expanded form of what we have for this particular polynomial. Okay, that will have again the following zeros, and again just the expanded form. Okay, we have to be fourth degree, and again the highest order variable term defines the degree of this particular polynomial expression. And let's see what we get. So you're looking for the factored and expanded form. of f of x given and we'll say that for the zeros. And we'll say that we have let's say the 0 is going to have a multiplicity of 2. And then for the others, okay, these are just have a multiplicity of 1. So we'll just say we have, we'll say we have negative 2 and positive 5. And for the degree, the lump sum degree, okay, so you have multiplicity of 2, okay, so you got second degree here, and with negative 2 and 5, each with a multiplicity of 1, so you have like 2 plus 1 plus 1, so you're going to end up with a fourth order polynomial expression. So just for the next few moments, let's see what we get for the factored and expanded forms of f of x. Okay, just in the case of laying the foundation, okay, we have with initiating the factors. Okay, so corresponding to 0, okay, we just have the letter x to represent 0. But now, with a multiplicity of 2, okay, we have x corresponds to 0, but with 0 having a multiplicity of 2, and we have not just x, but x to the second. And for what we have with negative 2, we can say that will originate from x plus 2. And as for 5, okay, we can say this comes from x minus 5. So these three items will set up the factored form. Okay, so you have f of x is equal to x squared times x plus 2 times the quantity of x minus 5. Okay. Now if we look into the expanded form, and say if we distribute x squared over x plus 2, I'm just going to have x minus 5 waiting to be multiplied. And we have with distributing, so we have x squared over x plus 2. So you have x cubed plus 2x squared. And we have times the quantity of x minus 5. And so we have carrying out the FOIL. Okay, so you have x cubed over x. Okay, so this will be x to the 4th. Outside product we'll have at negative 5x cubed. And we have inside product we'll have plus 2x cubed. And 2x squared minus 5. And minus 5 will multiply out to negative 10x squared. So we have, in the case of the expanded form, okay, so we have f of x, okay, we have is equal to x to the 4th minus 3x cubed minus 10x squared. Okay, so we'll be looking at expanding or determining polynomials from given zeros. I just want to mention, I think in a good chunk of the next upcoming section is going to involve working in reverse, where you're looking at determining zeros and their multiplicities from a given polynomial that is in expanded form. Let me kind of cap off with a case here. Okay, so if I were to determine the zeros, and multiplicities. And say we have f of x is equal to x to the fourth plus 4x cubed minus 12x squared. Okay, so if I work through this, okay, so you have f of x is equal to x to the fourth plus 4x cubed minus 12x squared. Okay, so if I look at factoring, okay, so the greatest common factor we have in the set is going to be x squared. And factoring out x squared, so we have x squared plus 4x minus 12. And this trinomial, we can factor even further. So you have f of x is equal to x squared times the quantity of x plus 6 times that of x minus 2. So this is going to be the factored form. I'm just going to rewrite this, just sort of emphasizing the degree. So for what we have in the case of the zeros. Okay, so for just x, we'll have 0. If you notice, you have x is raised to the second, so 0 is going to have a multiplicity equal to 2. And for x plus 6, okay, so I'm going to have negative 6. And x plus 6 is raised to the first, so that is going to have a multiplicity of 1. And we have with x minus 2, we have x is equal to 2, we have another 0, and x minus 2 is only a first degree, so that multiplicity is equal to 1.